Good morning, everyone. I'm Jian, and today I'm going to introduce FileMR, Rethinking RDMA networking for scalable persistent memory. And in this talk, I will introduce the challenges of combining two emerging technologies, RDMA and persistent memory, and introduce a solution that provides fast user-level RDMA access. This work is done while I was at UCSD, and along with Joseph Izraelevitz and Steve Swanson. So persistent memory, or PM, represents a new class of memory that's built upon emerging technologies such as PCM, STT-RAM, or Intel's 3D XPoint. So today we use DRAM as our main memory, and the persistent memory will be co-located with DRAM and is byte-addressable by the CPU, which means the user applications now is able to use a few instructions to finish data writing and persistence. And this will take about a few hundred of nanoseconds. And in comparison, if we want to do this on a block-based device like a fast SSD, it will at least take tens of microseconds to complete. So persistent memory also has higher density. You can have like terabytes of memory attached to a single socket. And like any storage, we want to have persistent memory access remotely. And since PM relies on low latency, RDMA seems to be the best fit for this. So the RDMA basically gives you the illusion of having DMA capabilities between two hosts. And under the hood, it's basically doing address translation and DMA for you on the RNIC and bypassing the CPU or the application running on the server node. So the most prominent feature is one-sided read and write, and that would be a good fit for persistent memory. However, we are observing that when running RDMA over persistent memory, we see several significant issues. The most important one is performance degradation. So if we run 4 kilobyte random writes over RDMA region, we'll notice that the performance quickly drops as you increase the size of the access region. And at 512 gigabyte, we are losing about 60% of the throughput. And there are also other issues such as allocation, protection, and naming. So to better understand this problem, we need to take a look at how virtual memory management is done on both persistent memory side and the RDMA side. So let's start with persistent memory. Applications access persistent memory through a file system, and this is usually is specifically designed for persistent memory or some existing file system with some optimizations. So after opening a file on the PM, the application will map the entire file into its address space and for the entire lifecycle. So because of a feature called direct access or DAX, the file system will create the mapping that directly points to the actual memory, so there is no page cache. After those control path operations, the application can simply issue CPU instructions, so the kernel is out of the loop unless we invalidate the page mapping. So if we look at the address translation here, the user virtual address is map backed by the file content, which is usually managed by the file system in extents. And since we are talking about terabytes of memory, and also there's aging issues with any file system, so the file system will use defragmentation such as garbage collection, and the operating system will also optimize the layout of the virtual memory using techniques such as the compaction in the transparent huge pages. Next, let's look at the RDMA side. So the basic unit for RDMA memory management is a memory region. So on the control path, the application can allocate some memory on its own, usually through malloc or shared memory or mmap, and register it as a memory region. So during this process, the RDMA driver will ping those page table entries between the user virtual address and the physical address. So this will allow the RDMA NIC to do the translation and directly from virtual to physical addresses. Let's walk through an example of and see what will happen if we glue the two pieces together. So now we open the file system will create some data structures that store the file metadata, including the file extents. And next, we will map the file into its address space. Although we are mapping the whole file, we are not actually creating any entries here because this is all on demand. But now, since we need to provide RDMA access, I will need to create a memory region. But because of the RDMA, how the way RDMA works, the RDMA driver will try to fault in every page and trying to create the page table entry for the entire mapping. And the whole user address space will be populated. So apparently you can see many issues with this, right? So there will be TLB pollution, and most importantly, this is very slow because we are talking about holding the VM lock, and sometimes there's a device lock while doing this. So there's it's serialized, and you can only do it. It will take about 25 minutes to map 1 terabyte of memory. And since the RDMA cannot go through a page table, it will usually create some a mirror of a flattened version of the page table in its managed memory, and we call this memory translation table. So now after this process, the mapping will be completely frozen, and the file system can no longer update the file layout. And now we have an incoming write. This write will be picked up by the NIC, and it will look up the address translation and find the MTT entry. So since the NIC often have some on-device buffer that can cache those entries because the memory access to host memory is pretty expensive. So as a result, we have a large amount of memories, and we will definitely have a performance issue here because the cache misses. So in summary, the Linux virtual memory system is not really designed for this kind of use case, right? So persistent memory is relatively new, and there have been a lot of optimizations in this, but unfortunately, those optimizations often require remapping and does not work with RDMA. And RDMA is also not designed for this kind of large-scale permanent mapping use case. And there are other issues that we discussed in the paper, but here we will focus on the VM issue due to the time constraint. So this issue is not new. There are a lot of research and product on this topic. So apparently, if we can design storage and networking in the same stack, we can put everything together, make some assumptions, we can build a holistic system that can work well without going through those constraints. And similarly, we can provide an indirection. For example, we build a distributed file system to use the POSIX interface, which does not handle the VM in directly to the user. And then we lose the most important feature of the persistent memory, which is byte addressability. And similarly, the NIC can use IOMMU to create a virtualized mapping, and then there can be a page, IO page fault, and then the NIC can fetch the entry on demand. The problem with that is this process is pretty expensive, and we need something like TUNIC to accelerate that, to learn the pattern. And finally, if we do physical address on wire, there are security issues. So the fundamental issue here is that both persistent memory file system and the RDMA are controlling the metadata management, right? So the translation is fundamentally conflicting between the two parts. One wants to be static, while the other one wants to be dynamic. And other roles, such as allocation, permission, and naming, are redundant and overlapping between the two components. So what we want to do here is we want to let the file system handle most of the tasks while letting the RDMA NIC to focusing on the remote access and to be less stateful. So because of the above issue, we are introducing a new type of memory region called FileMR. So with FileMR, the file system maintains the translation of the MR. So the translation is always initiated from the file system and propagated to the RDMA stack. So that means two things. First, the address used in RDMA, at least for FileMR, it will be decoupled with the virtual memory subsystem. It simply means a file offset. And second, how we interpreted the file offset is totally up to the file system. So we can implement permission and naming in the file system layer. So let's go through the previous example one more time to see how this works. The application will open the file, and now it will have the file in its user space, right? So then, the file descriptor in the user space, and then it can still write to the file system or expand it on the control path. And next, it will, instead of mapping it to its address space, it will just create a FileMR without any provisioning. So this will be like a constant operation. And the next, we will create a binding between a file and a FileMR. So the way we do it is currently through IO cattle to the file descriptor. So the file system will, internally will find those entries and establish some function callbacks between the file system and the RDMA library, and it will keep pushing the any updates to the file layout, which means you cannot control you cannot modify the file layout through the RDMA path. And incoming write from a remote node will contain file IDs and offsets. And additionally, we also introduced a new verb called append. So because append is often used in file systems and also for persistent memory, oftentimes we use red hat logs. So that's a very typical usage. So the way we implement that is to over-provision the memory region or use page fault. And the verb is similar to a send. So you will basically write into the end of a memory region and keep increasing the region size. And also, I have been talking about file system, but the notion of file system here is very loosely defined. So anything that can handles address translation and implements those function and callbacks is a file system. So for example, we can extend the libpmem, which is a user space PM library, to provide the access for, provides the functionalities for remote access, and then we can implement libpmem log, which is a logging mechanism based on libpmem to use FileMR. So since we are talking about file extents, so we need to have some range-based translation as well. So in this work, we are reusing a previous work designed for CPU TLB that uses range-based translation. So we are assuming we have some translation entries which contains the base offset and the size, and those are structured in the B tree, and we are not using addresses, and instead we're using page offset. So each address is corresponding to a page, so we can have a large enough space for addressing. So we implemented FileMR and range-based translation on SoftRocky. So SoftRocky is basically a software RNIC implemented on top of UDP. So the right side shows all of the changes we have made. So apparently we need to add some flags throughout the RDMA stack, but the most the added interface are only the IO cattle, which works as a bind, and the range-based API, which communicates between the file system and the RDMA stack. So since RxE does not have any caching, it just uses DRAM, right? So we implement the range-based translation as using some emulation. Basically we build an emulator here. And apparently this is a very primitive implementation, and we have lots of limitations here. So the most obvious one is we cannot measure end-to-end performance because the numbers are mostly caused by the UDP overhead. And also our current latency is higher than the real NIC because of the way we implement everything. So here is a quick evaluation. So if we compare the registration time for FileMR versus like allocating and the mapping on huge or 4 KB pages, we can see like a more than 2 magnitude time of saving. And if we compare the latency of like the log append, comparing FileMR versus the local libmem log append and RPC-based solution, as you can see, we are adding about 50% overhead to the local version, while the RPC you will need to persist on the remote side, so that will cost like 3 times of the overhead. And also, we evaluated our range-based translation using some like existing file system benchmarks, and the conclusions are the registration time and both the registration time and the MTT entry size can be greatly reduced by using a range like extend-based solution. Although if you have a very fragmented file, you will still have the like many entries. However, because the file already has the locality, so we can actually still save some like cache. We can have a better cache hit even with like more fragmented files. To conclude, persistent memory provides byte addressability, and RDMA also provide byte addressability. So, however, we find they don't mesh together easily, and we are proposing a FileMR, which is like a file-based RDMA concept, and along with the range-based translation. So that concludes my talk. Thank you.
Yeah, great talk. Chen from FutureWay here. Looks like the issue is not the RDMA, the issue is the translation, the paging concept that's introduced by file system.
Exactly. So the translation is one of the major issue here. We do discuss a few other issues in the paper, which, like, for example, you can like the naming, it might also become an issue if you want to like have persistent connections over power failures.
Then just another thought is with the appearance of the zoned namespace, which the storage will be append only, then we can get away from the paging concepts for files that has holes, has all these things, and we make everything much simpler.
Yeah, I think there are a lot of since we are talking like I think the industry is going towards like disaggregated memory. Like for example, we have the like what you just described, and also we have the CXL, which puts memory remotely. So this issue will become more applicable to DRAM as well. And I think if you can get rid of the paging, many of the problem can be solved.
We can discuss offline.
Yeah, thank you.